Okay, so cardiac muscle. Again, we are just going over a very brief overview, just comparing and contrasting cardiac muscle to skeletal muscle here. So we're not going to go too deep into this. We're just going to get the main things, the main points, and in AP2 you're going to go a lot deeper into it. But here's my representation of a cardiac muscle cell. So I've drawn it a little bit wider than it would be. It would be, a little bit more narrow than this. But I wanted to have enough room so you could see everything in here. And it's got some similarities to skeletal muscle. Namely, one, we've got our T-tubules, which I've drawn as just this sort of like crossing extensions here, which are going to carry the action potential throughout the entire cell, which skeletal muscle also has. Smooth muscle does not have T-tubules. So cardiac muscle and skeletal muscle are the only two that have the T-tubules. We also have sarcomeres. So this is a sarcomere. I just drew one on here, but remember when we have sarcomeres, they would be lined up end to end and all throughout the cell, filling up the cell entirely. So all the space within the cell. So that means we have our actin and myosin, and the actin and the myosin are going to be interacting in the same way with the sliding filament theory that they do in skeletal muscle. So we already understand how that works with the myosin heads binding to the actin and pivoting in towards the center for our sliding filament theory. So it's going to be exactly the same there. Also exactly the same is the idea that we have the action potential. It's carried through the T-tubules all throughout the cell very, very quickly. And when that action potential hits an area where the T-tubule is interacting with the sarcoplasmic reticulum, it's not the terminal cisternae in this case. Cardiac muscle does not have terminal cisternae in the sarcoplasmic reticulum. It just has sarcoplasmic reticulum, but we still have calcium stored there. So the T-tubule and the sarcoplasmic reticulum are going to interact in the same way that they do in skeletal muscle, which is when the action potential goes shooting down that T-tubule, it hits this little channel that's on the T-tubule. It's called a Dihydropyridine Channel, so it's a big word. It's just a very specific type of L-type calcium channel, which we went over before, a voltage-gated, long-lasting, slow calcium channel. And that dihydropyridine channel is linked to a ryanodine channel, which is on the sarcoplasmic reticulum. And when you open the ryanodine channel, that allows calcium to come out of the out of the sarcoplasmic reticulum into the cytoplasm. So now we have calcium all out here. It can bind to troponin, move troponin and tropomyosin away from the binding site on the actin. Cross-bridge formation happens, power stroke happens, and we shorten the sarcomeres. So very, very, very similar. Another difference with cardiac muscle, or a couple of other differences with cardiac muscle between them and skeletal muscle. They are innervated by the autonomic nervous system, so not the somatic. They are joined together by very specific cellular junctions called intercalated discs. And these consist of things that we have already learned when we talked about epithelial tissue, namely our gap junctions, which are going to allow our cells to do what? Which everybody should be just saying before I even say it, because you should all remember they allow cells to communicate, right? So hopefully you remembered that. If not, you will. And remember it for MP2. And we're going to see a little bit more in the nervous system also. So we have gap junctions as part of the intercalated discs, and then desmosomes, which would ring a bell from the epithelial system. Those desmosomes are just there to hold everything together. So that's different than what we have in skeletal muscle. Now, going back up to this fact that the cardiac muscle is innervated by the autonomic nervous system, there is another way that our cardiac muscle cells get a stimulus, and that is through pacemaker cells. And pacemaker cells do something called spontaneous depolarization. And what that means, and again, we haven't gotten this far to where we talk about the electrical activity of cells yet, but we are almost there. So we want to start to think about things in terms of ions moving across cell membranes and bringing their charge with them. And when they do that, they are essentially creating an electrical current. So anytime you have charged ions moving across a cell membrane, it's an electrical current. So when a cell spontaneously depolarizes, or let's just even think of it just as when it depolarizes, it means it gets more positive inside. When it does it spontaneously, it means it's doing that on its own without a stimulus. There's no particular stimulus required. So when a cell depolarizes, that is something that is going to tend to stimulate a cell, cause it to do whatever it is that the cell does. So in the case of a pacemaker cell, it would be firing an action potential. It's going to spread throughout the heart to other pacemaker cells and then eventually to the cardiac muscle cells that are responsible for contracting and pumping blood through the heart. When other cells depolarize, a muscle cell, that's an action potential in a muscle cell that causes it to contract. When a neuron has a depolarization, then that could cause it to have an action potential, which will cause it to release neurotransmitter. So we're going to see a lot of depolarization in the weeks to come. But when we are talking about our pacemaker cells, they're doing this without any sort of stimulus from the nervous system. So even if your nervous system, your autonomic nervous system, was just completely not doing anything, if it was just not stimulating your heart at all or not trying to slow it down at all, these pacemaker cells would still be spontaneously depolarizing, and they would be doing it at about once per second, which means that once per second an action potential would be spreading around your heart, causing all of this to happen in the muscle cells around it, which would essentially give you a heartbeat every second, which gives you a heart rate of about 60 beats per minute, which is a kind of normal, typical resting heart rate. Now, the autonomic nervous system comes in when it is time to speed it up or slow it down. So if you get, really excited or scared, or if you're exercising, things like that, one part of your autonomic nervous system is going to speed it up. If you're relaxing, you're sleeping, slowing your heart rate down, that would be a different part of the autonomic nervous system. So the autonomic nervous system can affect the pacemaker cells, but even if it's not, the pacemaker cells are still going to continue firing action potentials, causing them to spread and give you that happening in the cardiac muscle cells. Okay?